Hi, thanks for clicking on this video. In this one we will cover some details on how the Ode45 integrator works. First, I introduce something called the Butcher-Tabelau based on a simple example. This is a convenient way to write down the steps required for numerical integrators. Afterwards, we use that to cover how the Ode45 integrator works itself. After that, we take a look at Matlab's implementation, first the integration itself, afterwards the interpolation. The interpolation is used to provide simulation results on a smaller time scale and is used if you call the integrator like this, rather than with just start and end time. Its setup allows for parallel calculation and is a lot more efficient than just running the Ode45 integrator with the smaller time step. In this video I focus purely on how the integrator works, and stuff like an application example is in a follow-up video. I will link it or them in the video description as they are released in the future. In essence, the Ode45 is a multi-step integration method where the solution is calculated according to this Butcher-Tabelau here. The steps are being completed from top to bottom, one after another. This tableau is a compact representation of the equations to save a lot of equation writing. Let's get rid of it for now and derive it for a simple example first. Let's quickly repeat how a numerical integrator works in general. We start from our state here and are interested what our state is in a given step delta t. First we calculate the change of state with our differential equation evaluated at this point. The change of state is just a tangential line to this point here. Next, we move along this tangential line to calculate our updated state that lies in the future over here. Repeating this over and over again and recording all of the points in between gives us our simulation result. If we just use this single step, this would be the simplest form of an integrator, and we are done after a single step. Now, instead of just calculating this with one step, we can do the following, which gives us more accuracy down the road and allows for a bigger time step. We start by calculating the incline in our starting point, move alongside to the end point and calculate the state here. So far it's the same as before, but instead of being done now and continuing with the next time step, we instead calculate the incline here using the state we just calculated. Then go all the way back to our starting point. Now we use the incline we calculated at the start of the integration step and the incline at the end together to calculate our actual step, and we end up here. Comparing the result achieved with those two methods for a simulation of this system here, where we know the exact solution to be cosine of t, shows us that depending how big we make our time step greatly influences the accuracy of our simulation. As you can see here, if we adjust our time step to be larger or smaller, you can see how vastly different the accuracy of those two methods already is. The second method allows for a significantly bigger time step, and even though it requires more calculations for one step, it is overall faster because the step size can be way bigger. It is advantageous to formulate those calculations in form of a Butcher-Tabelau. For our method with two steps, it looks like this. It is advantageous to write it down like this because the method works the same way, independent how many steps we add. We can see the number of steps, so the number of individual k's our integration method has, by counting the number of rows above this line here. For this method we have two steps. Each of those steps represents a calculation of one of our ki values, so the inclines, that we use to assemble our final integration step out of. And we can see how those have to be done by looking at the rows themselves. The first k is calculated using the start time and start state. The second k is calculated as follows. The time we use for our calculation is the start time plus the value in this column here, and the state we use is the start state plus this weight here times the first k. At the end, we use the very last row to calculate our actual integrator time step, and the equation looks like this here. Our final endpoint equals the start point plus the span of our interval times all of the k's combined with the weights found in the last row. If we use a more involved integration method, like the Ode45 scheme does, we have a bigger tableau with more steps, but the general concept stays exactly the same. Let's look at the Butcher-Tabelau for the Ode45 method next and go through the first steps. Generally, the Ode45 uses two of those methods with a different number of steps. Then the error between the two is evaluated to determine if the actual time step by the integrator can be increased to save calculation time, or if it has to be decreased to ensure accuracy. There is a publication that explains how you can come up with the weights used in the Butcher-Tabelau. The publication is from Dorman and Prince, and that's why this method is often referred to as Dorman-Prince integration. I have put the citation to the publication in the description if you want to check it out. The Butcher-Tabelau for the first integration method used looks like this. Let's write down the first three equations of the method. Our first and second k are calculated quite similar to the previous example. We just use a smaller initial time step. For the third k, however, we now use this time step and already start to assemble the point for our state from the other two k's with respective weights added to them. You will notice that adding all of those weights together always leads to the same result as the time step over here. This is true for all the steps. The rest of the equation, so k4 to k6, results from the tableau as well, and the final actual integration step is calculated from the last line like this. After this step is completed, the Ode45 needs to figure out how accurate the result was and if the time step has to be decreased. To do this, a second method is run that contains one step more. Comparing the results of the two methods allows to estimate the error. If we now put the two tableaus next to each other, you can see that most of the entries are actually the same. So if we save our k1 to k6 values from the first method, we do not have to recalculate them over here. And we can save a lot of time overall. In order to calculate the error, all we have to do is calculate k7, and afterwards we do not even have to calculate the actual integration step, because we are only interested in the difference. Writing both equations down and subtracting them leaves us with this equation for the error, and this is all we have to evaluate. So all of this second step and error calculation is computationally quite efficient because we have already completed most of the math required. The error is then used to determine if the time step taken by the integrator can be increased so that we need fewer integration steps to reach our endpoint and save on calculation time overall, or if the time step has to be decreased in order to ensure that our error stays small enough and our results are still accurate. Let's take a quick look at the actual code of the implementation to check if that is how it is actually done. You can use open Ode45 in the command line to take a look at the code. The code you get might look different depending on the version of MATLAB you have. Here we have our inputs, where this is our ODE function containing the differential equations, and the rest of the inputs are additional options you can provide, but that's not important for now. Let's look at our steps of the integrator here. Here, the initial time step is calculated. I did not dig into how it figures out the starting time step exactly, but it is based on the total time interval that you provide the simulator with. In this step here, we calculate our first step, so the first Butcher-Tabelau. Here we calculate the 7th k value as mentioned before. In this step, we calculate an estimation of the error using the first method and the second. And down here, we check if the error is under an acceptable boundary or not. If it is not, we tell the integrator to repeat the step with a smaller time step, and if it is, we are done. This is repeated until we hit our final endpoint. We save the time points, the state, and also the k values for later. Those are required later for our interpolation step of the results. Afterwards, the simulation result is interpolated so that more intermediary points are returned to have a smoother display of the results. There is also a scientific publication alongside the algorithm that I will link in the description. It contains the sources for individual steps and describes the calculation in greater detail. We have now spent quite some effort ensuring that our time step used by the integrator is just right. If we now no longer call the integrator like this, but instead like that, our simulation results will get returned with the time resolution defined here. The integrator step for both calls, so the real Ode45 part, is exactly the same. The only difference is the interpolation performed after the simulator part. The second Ode45 call interpolates the result on the time resolution we provided with. Let's check out how the interpolation works mathematically. When running the Ode45 integrator, the time, state, and all of the calculated k values from the Butcher-Tabelau are saved for each time step. Afterwards, to interpolate, this equation is used with the parts being the state at the start of the interval, the time span between two Ode45 interpolation points, the corresponding k values for this time step. Here in this matrix Bi are weights that we have to multiply all of the k values with. And back here is the time span of the interval normalized to be 1. So if our time span for this interval is this up here, this value will just look like this. Visualizing this for a system with 3 states will look something like this. We can now multiply k and Bi to shorten this a little bit. Here we have state 1, 2, and 3, and this is the first, second, third, and so on time step. If you are interested in, let's say, this point here, the calculation just comes down to the start point plus this row times this column. And this is a lot quicker than running a full Ode45 integration step. Even better, all of the interpolation calculation can be run in parallel to save calculation time. Here is the code from Matlab with the different parts of the interpolation function marked in color. What is weird about this? That if you want to look at this code, you have to use breakpoints in the code and the step into function, because for some reason you cannot open this with open NTRP45. It just does not find it. As you can imagine, this interpolation is finished a lot quicker than running the simulation with a smaller time step, especially considering that no more evaluation of our ODE function is required now, because we can just use the values calculated previously. Alright, thank you for watching the video till the end. I hope you learned something. If you found this video helpful, interesting or useful, tell me by hitting that like and subscribe button and leave a comment. In the next video, I will show you a simulation example where we apply the knowledge gained here to fix an issue, because there is a case where this method can cause issues. The plan for the video after that is to cover Lagrange's principle and how we can use that to derive the equations of motions for a system. See you next time, bye for now.